Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Classical Thermodynamics of Phase Equilibria Part 2. Since it is a continuation of previous lecture, before going into the details of today's lecture, we will be solving a few example problems based on the things what we have discussed in the previous lecture. Volume coefficient of expansion of mercury at 0 degree centigrade is given. The coefficient of compressibility Kt is also given. If mercury were heated up from 0 degree centigrade to 1 degree centigrade in a constant volume system, what is the pressure change or how much pressure would be developed, that we have to find out. Okay. This coefficient of compressibility is given Kt, and then volume coefficient of expansion, this alpha p is also given, right. So, that means if we need to find out delta p. Okay. So, that means dou p by dou v we have to find out actually. So, given that Kt is equals to minus 1 by v dou v by dou p at constant t, that is given. Dou p by dou t at constant v, we can write it as minus dou p by dou v at constant t multiplied by dou v by dou t at constant p, right. So, but further we also know that alpha p is equals to 1 by v dou v by dou t at constant p, that means this is related to this particular term, and then also it is given that Kt is equals to minus 1 by v dou v by dou p at constant c, that means this particular term is related to this one. When we use this one here in this equation, then we have dou p by dou t at constant v is nothing but alpha p by Kt. Alpha p is given in the problem, Kt is given, so we substitute here this thing. Then you will get 33.8 bar per degree centigrade. Now, delta t is 1 degree centigrade. So, that means delta p is equals to alpha by Kt delta t, that is nothing but whatever alpha p by Kt is there, that itself would be the pressure that would be developed if you change the temperature from 0 degree centigrade to 1 degree centigrade. Another example, find expression for these things for a gas whose behavior can be described by this equation. There is a gas, non-ideal gas is there, so that equation of state of that gas is given by this equation. Then what are the corresponding expression for these 5 partial derivatives? In addition to those things, also we need to find out the absolute changes, right, those things we have to find out. So, first we have to make use this equation. So, the equation given is P multiplied by V by N minus B is equals to RT. So, this equation if you rearrange, you can write P is equals to nRT by V minus Bn, and then same equation you can write V is equals to Bn plus nRT by P. We are writing this one because we need to find out dou S by dou V at constant T, right. But from the Maxwell relation, dou S by dou V at constant T is nothing but dou P by dou T at constant V. So, that means P is already there. So, this equation if you differentiate with respect to T at constant V, then you will get dou P by dou T, that is nR by V minus Bn. So, that first one is already found. Similarly, dou S by dou P we have to find out, and then from the Maxwell relation again dou S by dou P at constant T is nothing but minus dou V by dou T at constant P. So, V expression we are already having. So, this expression if you differentiate with respect to T at constant P, you will get dou S by dou P at constant T. So, dou V by dou T is nothing but nR by P. So, dou S by dou P at constant T is nothing but minus nR by P. Likewise, we can find other properties also, because we have du is equals to T ds minus P dV. From this equation, dou U by dou V at constant T can be written as T dou S. This should be from here actually dou U by dou V at constant T should be T dou S by dou V at constant T minus P. But from the Maxwell relation, dou S by dou V at constant T is nothing but dou P by dou T at V, that we already found nR by V minus Bn. So, nR by V minus Bn multiplied by T minus P. Now, this nR T by V minus Bn is nothing but P from here. equation of state. So, P minus P is equals to 0. Third one is also found, and the next one is dou u by dou p at constant t. So, by product rule we can write it as dou u by dou v multiplied by dou v by dou p. Since dou u by dou v is already 0, so this is again going to be 0. Fourth one is also found. Another relation that we have, dH is equals to TdS plus VdP. We need dou H by dou P. So, from here what we can have, dou H by dou P at constant T, then T dou S by dou P at constant T plus V dou P by dou P is nothing but 1. But this dou S by dou P at constant T is nothing but minus dou V by dou T at constant P, that is nothing but minus NR by P, minus NR by P multiplied by T plus V is here. Okay. So, then we get minus of minus V minus Bn plus V, because N RT by P from this relation is nothing but V minus Bn from the equation of state that is given, from the equation of state that is given, and then this V is as it is. So, then this Bn is there. So, this partial differential quantities obtained. So, then absolute quantities can be obtained by just by integration. From here delta S should be nothing but dou P by dou T integral dou P by dou T dou V, because we know here this dou S by dou V is nothing but dou P by dou T at constant V from the Maxwell relations, right. So, that we have simply written here dou S by dou V at constant T is nothing but dou P by dou T at V. Dou P by dou T we already got it as this one. Now, integrate this equation. So, you will get ln V minus Bn, then V changing from V1 to V2, some V1 to V2 they are not given. So, this equation we are having. So, that means minus NR ln P1 by P2 is delta S. Similarly, delta U we have seen that delta U from this equation, as you know, we have already have this equation dou u by dou P is nothing but minus dou u by dou V multiplied by dou V by dou P, but dou u by dou V is 0, that we already derived in the previous slide. So, overall this delta U is going to be 0. Similarly, delta H we have seen that relation, you know, dou H by dou P in the previous slide we derived, this is nothing but minus T dou V by dou T plus V. So, this equation if you integrate, then you have this one, dou V by dou T is nothing but Bn, and then you substitute all these equations here, whatever this expression, this particular expression we found it as Bn, minus T dou V by dou T plus V we found it as Bn in previous slide, Bn dP integration if you do Bn P2 minus P1. Then finally, delta G is nothing but delta H minus T ds. So, that you substitute. So, then you will get this final delta G expression, and then delta A is nothing but delta U minus T ds. So, delta U you already calculate, delta S you already calculated. So, substitute here you get delta A, simple and straightforward. Example number 3, the residual volume alpha is the difference between the ideal gas volume and the actual gas volume and is given by alpha is equals to RT by P minus V. For a certain gas, alpha has been measured at 100 degrees centigrade and at different molar volumes. The results are expressed by the empirical equation alpha is equals to 2 minus 3 by V square, where V is in liter per mole. The velocity of sound omega is given by omega square is equals to minus Gc k V square dou P by dou Vt, right. Calculate the velocity of sound for this gas at 100 degree centigrade when its molar volume is 2.3 liters using k is equals to 1.4. The molar mass is also given. So, only thing that if you wanted to know the omega, you should know what is dou P by dou V. So, alpha expressions given, two expressions are given, we can make use of these equations to get P is equals to function of V, and then we can find out dou P by dou V at constant T. then substitute here, simple. So, alpha is given like this. If you rearrange this equation, P is equals to RT by alpha plus V. Alpha is given for this system as 2 minus 3 by V square. You can rearrange this equation, so you will get this one, and then dou P by dou V at constant T, if you do, you will get this equation. Now, in this equation R, T, V, etc., everything are known, substitute here. So, then you will get, because V is given, T is given, R is given, R is known, molar mass is also given. So, when you substitute all these things, dou P by dou V at constant T, you will get this value. And then we need to know omega, but omega square expression is given. Here also GC is given, K is given, V is known, dou P by dou V we just calculated. Substitute all of them, then you will get omega square is equals to 24621. That means omega is roughly 157 meter per second. Okay. Simply making use of given equation of state to get the required information. Final example problem now. Second virial coefficient B of a certain gas is given by B is equals to small b minus A by T square, where A, B are constants. Compute the change in internal energy for this gas in going at temperature tau. The temperature is going to change from certain temperature to tau temperature, from very low pressure to a pressure pi. So, delta P is nothing but pi, delta T is nothing but tau. Then what is the change in internal energy? Delta U you have to find out. Okay. Equation, this virial equation is given, Z is equals to PV by RT is equals to 1 plus BP by RT is nothing but virial equation of state, it is given. So, this equation we have to make use. So, we need du. So, from here actually du is nothing but TdS minus PdV for a closed system, because here exchange of matter nothing is mentioned. So, then obviously we can take it as a kind of closed system. So, from here this equation, at constant temperature dou U by dou P, if you do at constant temperature, you can have T dou S by dou PT minus P dou U by dou PT. S we do not know, but dou S by dou P at constant temperature is nothing but minus dou V by dou T at constant pressure from the Maxwell relation, right. This is coming from the Maxwell relation, and then this term is already there. Now, we know from the virial equation of state that is given, Z is equals to BP by RT is equals to 1 plus BP by RT. Z is equals to PV by RT is equals to 1 plus BP by RT is given. From that V you can write as function of temperature, pressure, and then get the differentiation. So, this is given. Now, this equation you can write like this. So, in terms of V you can write like this, and then this capital B is given like this, B minus A by T square, that is also given. So, from here dou V by dou T if you do, you will get this one, dou V by dou P if you do, you get this one. So, dou U by dou P at constant temperature is nothing but minus T multiplied by dou U by dou T is nothing but R by P plus 2A by T square, T cube, minus P into dou V by dou P. Dou V by dou P at constant T is nothing but minus RT by P square. So, when you simplify, minus 2A by T square you will get. Now, delta P is nothing but pi. So, delta U is equals to minus 2A, and then temperature is tau, temperature is changing to tau, then that means 2A by tau square, and delta P integral 0 to P. P is changing from very low pressure to pi. The low pressure let us take 0 because it is not given. So, then when you integrate this one, minus 2A tau square multiplied by P, you will get P pi minus 0. So, that is pi you are getting. So, this is the change in internal energy. We have been discussing classical thermodynamics of phase equilibria. So, how to fix the state of equilibrium for the system that we have taken, in which two or more than two phases are coexisting and these phases are equilibrium. So, how to fix the state of equilibrium for these problems, equilibrium problems, right. So, that can be done using the Gibbs phase rule. The second one is that we have been discussing that the chemical potential of each component is equal amongst all coexisting phases, right. Those phases which are at equilibrium, those things we are discussing. So, those derivations we are going to do. describing state of phase equilibrium. In general, in phase equilibrium problem, what is the aim? Aim is to relate quantitatively the variables that describe the state of equilibrium of two or more homogeneous phases that are free to interchange energy and matter. Gibbs phase rule is used to define number of intensive properties that must be specified to fix the state of equilibrium without any ambiguity. So, what is this Gibbs phase rule? This we have to first see, right. So, then how to find out that how many number of intensive variables has to be fixed in order to define the state of equilibrium without any ambiguity, those things that we are going to see in this Gibbs phase rule. So, let us say consider a heterogeneous system containing pi number of phases and m number of components at equilibrium with respect to the heat transfer, displacement of volume and mass transfer as follows, right. So, what we have a kind of heterogeneous system which is a closed system, because we know that equilibrium processes are the whatever the equal chemical potential behavior whatever we take, that is valid only for closed system. So, what we do? We take a heterogeneous closed system, right. But within this one we are having several phases which are homogeneous, right. So, let us say for simplicity we take two phases. We take a liquid phase L and then there is a vapor phase V. Okay. So, the properties, the whatever the density etc., those properties within the liquid are constant, uniform. So, whatever this liquid phase is there, that we can take it as a kind of one single homogeneous phase, right. And then vapor, whatever the properties of the vapor, the density etc., those properties within the vapor are again same, same within that vapor phase, but they are different from vapor to the liquid phase. So, then vapor phase can be taken as a kind of separate homogeneous phase, and there exists a kind of equilibrium amongst them. Before attaining the equilibrium, obviously the constituents from the liquid may be going to the vapor phase, and then similarly constituents of the vapor phase may be coming to the liquid phase depending on the degree of transfer of the species. Once the equilibrium is established, there will not be any kind of tendency to exchange the matter as well. So, here within this heterogeneous system what we have a kind of two homogeneous phases, right, and then there is a kind of exchange of matter as well, right. So, that is the reason within this heterogeneous closed system we can have a kind of we can see the equilibrium problem, we can discuss the equilibrium problem. So, as per the definition, this as per the basic that equilibrium problem or phase equilibrium is valid only for the closed system. So, what we are doing, we are taking a heterogeneous closed system. Within that heterogeneous closed system we are having different homogeneous phases. Okay. Now, here within this heterogeneous system we have a kind of internal equilibrium with respect to the heat transfer or that is thermal equilibrium. We also have displacement of volume, that is also at equilibrium, that is mechanical equilibrium is there, and then with respect to mass transfer as well there is a kind of equilibrium, that is chemical equilibrium is also there. So, this heterogeneous closed system we can say it is at the equilibrium if there is a kind of internal equilibrium with respect to heat transfer, that is thermal potential, with respect to the displacement of volume, that is the mechanical potential, and then a kind of with respect to the mass transfer, that is with respect to the chemical potential. So, that means this thermally equilibrium is established, and then mechanically also equilibrium is established, and then chemically also equilibrium has been established within this heterogeneous system. Then we can say that the system is heterogeneous system, that the heterogeneous system is at equilibrium. Okay. So, now for this case I have explained this one only for 2 phases. Now, let us take a common case of pi number of phases and n number of components. So, then what are these relations? What are these equilibrium relations are existing, those things we are going to see now. So, with respect to the heat transfer, what we have temperature has to be equal in all the phases if the thermal equilibrium is established. That means, T of phase 1, T of phase 2 should be equal, and then similarly that should be equals to T of phase 3 and so and so T of pi, that is temperature in all the phases should be equal, right. So, there because there are pi number of phases. Okay. So, then what we have T1 is equals to T2 is equals to T3 and so and so is equals to T pi. So, this is true if there is a kind of a internal equilibrium with respect to the heat transfer process. Now, similarly with respect to the internal equilibrium with respect to the displacement of volume or with respect to the mechanical potential, if there exists internal equilibrium, then what we have? We have this P1 should be equals to P2 should be equals to P3 and so on so should be equals to P pi, that is pressure in each phase should be equal. That is what the thing that you can understand here if there is a kind of a internal equilibrium with respect to the mechanical potential. Okay. Now, similarly one can have intuitively chemical potential for m number of components as well. So, that is we know the chemical potential of each component should be equal in all the phases. So, let us say for the component 1, the chemical potential of component 1 in phase 1 should be equals to chemical potential of component 1, the same component, but in phase 2 that should be equals to chemical potential of the same component 1 in phase 3 and so on. So, the chemical potential of same component 1 in pith phase, right. So, that is the chemical potential of first component should be same in all phases 1, 2, 3 and so on so up to pi, right. Similarly, for the second component also the chemical potential of that particular component should be same in all the phases. So, that is mu 2 in phase 1 should be equals to mu 2 in phase 2 should be equals to mu 2 in phase 3 and so on. So, mu 2 should be equals to that one that should be equals to mu 2 in phase pi number of phases are there, right. So, likewise if you keep on constructing for all m number of components like this. So, you can have mu m let us say for the mth component m number of components are there. So, last component let us say m. So, for the mth component its chemical potential in phase 1 should be equals to its chemical potential in phase 2, that should be equals to its chemical potential in phase 3 and then likewise that should be equals to chemical potential of that particular mth component in phase 5, right. So, this is how we can see if there is a kind of internal equilibrium with respect to the mass transfer also. Okay. So, this relation what it says, first relation it says system is in internal equilibrium with respect to temperature, and then second one this says the internal equilibrium with respect to the pressure, and then this relation says internal equilibrium with respect to chemical composition or the mass transfer. Okay. So, now how many relations are there here? So, what we can say here with the pi number of phases are there. So, we can say pi minus 1 relations are there for the heat transfer part. Similarly, how many relations are there? Pi minus 1 relations are there for the mechanical equilibrium part, and then for chemical potential point of view or the internal equilibrium with respect to mass transfer point of view, how many relations are there? There are m number of components are there and then pi minus 1 relation for each component. So, that is how many relations are there totally? Pi minus 1 multiplied by m plus 2 number of equilibrium relations are existing. This is very much essential in order to find out the degrees of freedom that are to be fixed in order to fix the state of equilibrium for that given system. Okay. Now, total number of intensive variables, how many are there? There are m number of components, okay, and there is a temperature, pressure. So, m plus 2 are there for each phase, and how many phases are there? So, there are pi number of phases. So, pi multiplied by m plus 2 number of intensive variables are there, but all of them are independent, that we have to check. Not obviously not all of them are independent, because let us say composition wise, if you say let us say x1, x2, x3 etc., that I am doing up to xm, right. So, m number of components are there, right. So, let us start with binary mixture. If you have x1 and then x2, so x1 plus x2 is equals to 1. So, if you know x1, obviously x2 can be known. So, that means only out of this x1 and x2, only one of them is independent variable, other one is not, right. Similarly, let us say if you have a tertiary component mixture, so then x1 plus x2 plus x3 should be equals to 1. That means out of these x1, x2, x3, if you know any two, third one can be found, right. So, that is the reason all of them are not independent variable. All of these many intensive variables, not all of them are independent, only m minus 1 multiplied by pi, those things are independent variable, and then m minus 1 and then plus 2 for the temperature multiplied by pi. So, that is pi multiplied by m plus 1 number of variables are only independent variable. So, in this relation whatever this 2 is there, that is for that corresponds to temperature and pressure. So, total number of independent variables are how many? Pi multiplied by m minus 1 plus 2, that is pi into m plus 1 are there. And then total number of equilibrium relations, how many? That we have already seen in the previous slides, they are m plus 2 multiplied by pi minus 1. Right. So, these are we are generally doing. So, just for a cross check, what we do? We take a system where there are two phases are there, that is pi is equals to 2, and then two components are there, that is m is equals to 2. Then how many relations should be there? So, according to this equation, m is 2 and then pi is also 2. So, 2 plus 2 into 2 minus 1, that is 4. 4 relations should be there. So, what are those 4 relations? That is T in phase 1 should be equals to T in phase 2, that is one relation with respect to the internal equilibrium with respect to the heat transfer. Then P in phase 1 should be equals to P in phase 2, that is internal equilibrium with respect to the mechanical potential. And then there are two components. So, chemical potential of component 1 in phase 1 should be equals to chemical potential of component 1 in phase 2, that is one relation. Then for the similarly for the second component also, chemical potential of second component in phase 1 should be equals to chemical potential of second component in second phase. So, there are those many relations are there. So, 4 relations are possible here. Okay. So, that is just to cross check whether are we missing any equilibrium relations or are we adding more equilibrium relations, like that. For that purpose only this manual cross checking we are doing. Let us say if you have 3 phases, that is pi is equals to 3 and then 2 components are there, that is m is equals to 2, then 2 plus 2 multiplied by 3 minus 1. So, that is 4 multiplied by 2, 8 relations should be there, right. So, with respect to the temperature, with respect to the heat transfer process, T1 should be equals to T2, that should be one relation, and then another one is T1 should be equals to T3. Okay. So, that means T2 will automatically be equals to T3. So, T2 is equals to T3, that will not be a kind of independent relation, it is already established. If we are writing that one as a kind of additional relation, so that will be we are counting it 2 times. If we are saying T1 is equals to T2 and T1 is equals to T3, it is obviously it means that T2 is equals to T3. Okay. Same is for the pressure, that is internal equilibrium with respect to the mechanical potential. P1 should be equals to P2 and then P1 should also be equals to P3. So, that means obviously P2 should be equals to P3, right. So, that is how we can see. So, how many relations are there? Pi minus 1 relations are there for the temperature and then pi minus 1 relations are there for the pressure also. So, pi is here how many phases are there? 3 phases. So, 3 minus 1 is 2. So, here also 2. And then coming to the chemical potential, the system is having 2 components. So, for each component mu 1 in phase 1 should be equals to mu 1 in phase 2. Similarly, mu 1 in phase 1 should be equals to mu 1 in phase 3. So, that means obviously we are saying mu 1 in phase 2 should be equals to mu 1 in phase 3 indirectly. So, that we cannot write as a separate relation, otherwise that will be counting one extra relation. Okay. So, mu 1 in 1 should be equals to mu 1 in 2 and mu 1 in 1 should also be equals to mu 1 in 3. That implies that mu 1 in 2 should be equals to mu 1 in 3. Okay. Same for the second component, mu 2 1 should be equals to mu 2 2 and then mu 2 1 should be equals to mu 2 3. So, that means mu 2 2 should be equals to mu 2 3. That means 4 relations are here also, 2 here, that is pi minus 1 into how many 2 components are there? For component 1 we are writing 2 and then for component 2 also we are writing pi minus 1 2 here. So, overall 8 relations are there. So, that you can cross check that here total number of equilibrium relation that we get m plus 2 multiplied by pi minus 1, right. So, now Gibbs phase rule, what it says, the degree of freedom in the sense that the minimum number of intensive variables that should be fixed in order to fix the state of equilibrium without any ambiguity. Without any ambiguity, that means you will not be having any difficulty to find out remaining intensive variables if you fix these many intensive variables, right. So, how to find out these intensive variables is nothing but the degree of freedom. So, that should be the number of independent variables minus number or relations or restrictions, that is equilibrium relations, how many equilibrium relations are there. So, we have already seen pi multiplied by m plus 1 number of independent variables are there, that is not the total number of variables, that is the total independent variables, and then number of relations we have seen m plus 2 multiplied by pi minus 1. So, if you subtract these 2 quantities, you will get degrees of freedom. So, that comes out to be f is equals to m minus pi plus 2. This is nothing but Gibbs phase rule, right. It gives information that how many minimum number of intensive variables should be fixed in order to fix the state of equilibrium for the given system. Okay. Let us say if you have a binary system and then 2 phase binary system. So, then number of degrees of freedom f should be how much? M minus pi plus 2, that is 2. So, what are the total number of variables, intensive variables? Temperature, pressure, let us say these phases are vapor and liquid phases, then x1, x2 and then y1, y2 are there, but since these are only 2 components. So, if x1 is known, so x2 is already known. So, this is not independent variable. Similarly, if y1 or y2 is known, the other one will obviously known. So, then out of these 2 only one is the independent variable. So, how many independent variables are there? 4 independent variables, 4 intensive variables are there which are independent. That means, out of these 4 variables, if you fix 2, that is degrees of freedom is 2. Out of these 4 variables, if you fix 2, remaining 2 you can find out using the principles of phase equilibrium without any difficulty. That is what it means by this Gibbs phase rule. That information this Gibbs phase rule will give you. So, that is out of these 4 variables, let us say temperature, pressure, x1 and y1. If you fix any 2, then remaining 2 you can easily find out without any difficulty using the phase equilibrium principles. That is the importance of Gibbs phase rule. Okay. Next, we see proof of equal chemical potential of every component in each phase of the system, that we have been discussing for a couple of lectures. Though we know that chemical potential of each component should be equal in each phase, can we prove it? Can we prove it? There are n number of phases which are coexisting, and then these n number of phases are having m number of components, let us say. So, for each component the chemical potential should be equal in amongst all these m phases. Whatever the m number of phases are there, in all these phases if you calculate the chemical potential, that should be coming out equal one constant single value for each component. Can we prove that one? So, that is what we are going to do in a simpler manner. There are a number of ways that you can find in different textbooks, but we take a one which is a kind of established one. Equilibrium processes are identified with reversible processes, that we know, that is holds for reversible processes only, and then criteria for equilibrium in a closed system is that U is a minimum or it decreases. Okay, and that any variation in U at constant total entropy and total volume that vanishes. So, that means any variation in U at constant total entropy and total volume vanishes, that is du at constant S V should be 0 for reversible processes. If it is irreversible process, then it should be less than 0. Okay. This we know, right. So, this is true for a closed system. What you have, du S V should be equals to 0 for reversible process. If the process in the closed system is reversible, then du at constant entropy and constant volume should be 0. That means there will not be any change in internal energy of the system. Okay. This also we have discussed, we derived this relation in the previous lecture. The total differential du by summing over all phases for multiple phases. Actually, for one single phase, what we have seen in this relation is nothing but du is equals to T ds minus P dV plus sigma mu I dni. This is what we have seen for one single phase, that previous in one of our previous lecture, this we derived. Let us say there are n number of phases, multiple phases are there. So, then if you write this total derivative for energy of the internal energy of the system, then how do you write? You write du is equals to sigma T alpha ds alpha minus sigma P alpha dV alpha plus sigma of sigma mu I alpha dni alpha. If you write for only one phase, it is you will have equation this one that we have already derived in previous lecture. If you have n number of phases are coexisting, and then system is a closed system, and then process occurring that in that closed system is a kind of reversible process, then we have a du is equals to sigma T alpha ds alpha minus sigma P alpha dV alpha plus sigma alpha of sigma mu I alpha dni alpha. Okay. So, now where here alpha in this equation is a phase index that may be changing from 1 to pi number of phases, and then I stands for the component index, and there are m number of components, let us say 1 to m. Now, let us expand this equation. Let us expand this equation for n number of phases and m number of components. So, for the first phase, phase 1, how you can write this equation? T1 ds1 minus P1 dV1, and then the third term in the RHS of this equation, it is having several terms, that is mu1 1 dn1 plus mu2 1 dn2 1 plus mu3 dn3 1 plus and so on, so mu m 1 dnm 1, that is in phase 1 m number of components are there. In phase 1 the superscript 1 stands for the phase 1. In the phase 1 n number of components are there, that subscript 1, 2, 3 etc. that is number of components, m components are there. So, all that whatever the sigma mu y dni is there, that is what this one for the phase 1. Similarly, if you write for the phase 2 T2 ds2 minus P2 dV2, and then within the second phase m number of components are there. So, whatever the sigma mu I dni for the second phase is this one, that is mu 1 2 dn 1 2 plus mu 2 2 dn 2 2 plus and so on, so mu m 2 dnm 2. So, like that if you keep writing for n number of phases, nth phase let us say you have Tn dsn minus Pn dvn plus in the nth phase m number of components are there, because all these m number of components are distributed among all these n number of phases, and these phases are coexisting and these phases are at equilibrium. So, then for that third part is for the nth phase, that mu 1 n dn 1 n plus mu 2 n dn 2 n and so on. So, mu m n dn m n. So, m stands for this number of components, n stands for the number of phases that are present, nth phase. Okay. Superscript n whatever is there, that indicate for the phase, okay, and then subscript m 1 to m etc. that indicates for the components. So, this is the du of the closed system that we have taken. Okay. Now, we know individual variations, that is ds1, ds2 etc., dv1, dv2 etc., dn1 in phase 1, dn1 in phase 2 etc. are subjected to constraints of constant total entropy, constant total volume and constant total number of moles of each species. What does it mean? That means ds should be 0 because constant entropy, and then dV should also be 0 because constant value, and then sigma dni should also be 0 because the total number of moles are also constant, right. And then ds is nothing but ds1 plus ds2 plus ds3 and so on, so dsn, the superscript n again for number of phases. So, that should be equals to 0. Similarly, for V, dV is nothing but dV1 plus dV2 and so on, so dVn should be equals to 0. So, similarly, sigma dni alpha should be equals to 0 because dni alpha and so on, so dni m should be equals to 0, and then this I stands for 1 to m number of components, right. So, here in above equations how many independent variables are there? There are m number of components and there is a m this for this one, and then there is a s and v, and how many phases are there? Pi number of phases are there. So, m plus 2 multiplied by pi number of independent variables are there, and then how many constraints are there? M plus 2 constraints are there. So, because for m number of components m constraints are there like this, this is only for one component I have written like that, m component m are there, and then 2 constraints are there for this s and v. So, that m plus 2 constraints are there. Okay. But equation for du may be written in terms of m plus 2 fewer independent variables by using the constraining equations to eliminate, for example, ds1, dv1 and m dni 1 like this. What does it mean by? Let us say from here this equation, we have ds1, we can write it as minus of ds2 minus of ds3 and so on, so minus of dsn we can write, that means one relation is reduced. Like that you can write for ds2 also, ds3 also you can write, but you can write only for one. Similarly, here also you can write, let us say if I write for dv1, so that should be equals to minus dv2 minus dv3 minus dvn, like this we can write. So, here also one is reduced. Okay. And then likewise here also in these relations, how many relations are there? This is nothing but m number of relations are there. From here we have a m number of relations are there. Okay. So, from each of these, if you out of these relations, if you can write like for each one dn1 alpha is equals to minus dn1 2 minus like dn1 1 should be equals to minus dn1 in phase 2 minus dn1 in phase 3, like this you can write. So, if you count all of those variables, you can have for m number of components m relations, and then for ds dv 2 relations, that is m plus 2 relations you can reduce. You can define that equation for du, you can write in terms of m plus 2 fewer independence, lesser m plus 2 number of less, those many less number of independent variables you can use for writing this du equation by using these constraint equations, so that to eliminate ds1, dv1 and then m dni1 like that. Okay. So, this is important one. So, because from this point from based on these relations only, whatever the way we are writing this ds1 and dv1, we are going to prove that T1 is equals to T2, P1 is equals to P2, and then mu1 1 is equals to mu1 2, etc., those kind of thing that we are going to prove here. So, this results in terms of pi minus 1 multiplied by m plus 2 independent variables, that is all the variations expressed as ds alpha, dv alpha, dn alpha are then truly independent, because certain variables are eliminated by using constraints or relations that we have here. Okay. So, let us make use of these reduced independent variables, or the eliminating certain variables by using these relations, whatever the benefit is there, that benefit we make use in writing this du. Whatever the du that we have written previously is this one, right. This is the du relation that we have written in the expanded form previously, without using the without eliminating ds1, dv1, etc. Okay. Now, what we do, we have this relation ds1 ds is equals to 0, and ds is nothing but ds1 plus ds2 and so on, so dsn. So, what we can write from here, ds 1 is equals to minus ds2 minus ds3 and so on, so minus dsn. This du is nothing but whatever we have done, sigma t alpha ds alpha minus sigma p dv p alpha dv alpha plus sigma of sigma mu I alpha dni alpha. This expression whatever we have for m number of phases, so that we expanded like this in one of the previous slides. So, the same thing I have written here. Now, what I am going to do in this relation, in place of ds1 I am going to use this expression. Okay. So, T1 multiplied by minus ds2 minus ds3 and so on, so minus dsn, right. So, first let us concentrate only temperature terms. So, then what I do now here, already there is a T2 ds2, right, T2 ds2 is here. So, and then now here T1 multiplied by minus ds2 is there. So, this I can write T2 minus T1 multiplied by ds2. This I can write it now, right, because now ds1 is replaced by minus ds2 minus ds3 and so on. So, So, minus ds2 into T1 is minus T1 ds2. There is already T2 ds2 is there. If I take ds2 as common, ds2 multiplied by T2 minus T1 I can write. Same thing I can write for wherever this T3 etc. are there. Okay. So, that is how we can do. Okay. Now, in place of P1 dV1, what I do? I will do the same thing. So, in place of dV1, now I use this relation because dV is equals to 0, that is constant volume, right. When I use this one, minus dV2 minus dV3 and so on, so minus dV, and that is what we are having. Now, already there is a P2 dV2, right. So, what I do, P2 dV2 is there, and now this P1 multiplied by minus dV2, and there is a minus 1 here. So, plus P1 dV2. So, minus P2 plus P1 dV2, like this I can write. Okay. So, similarly, for the first component, since the number of moles of each component are also constant in the system. So, in place of dN1 1, I can write minus dN1 2 minus dN1 3 and so on, so minus dN3. So, that means, right. So, that means here what I do, in place of this mu1 1, this is multiplied by dN1 1. So, in place of dN1 1 minus I write minus dN1 into minus dN1 in phase 3 and so on, so minus dN1 in phase n, let us say number of phases. So, now here what I can say, out of these two, there is already mu1 2 dN1 2, that I write it here. Out of these two, what I do, mu1 2 multiplied by dN1 2, and then here minus mu1 dN1 2 is there. So, that I can write minus mu1 1 this multiplied by dN1 2. This is how I can write. Like this, if I write for all other variables also, all other remaining terms also, then I write together them like this, I will be having like this one as I proved here, T2 minus T1 ds2 minus of P2 minus P1 dV2 or plus P1 minus P2 dV2, either way you can write. So, minus of P2 minus P1 dV2, and then for the first component also mu1 into minus mu1 in phase 1 multiplied by dN n1 and so on. So, for the mth component mu m2 minus mu m1 dN m2, like this you can write, right. So, like this, if you keep on writing, for other terms also like this series will continue, right, until you write for all the terms which correspond to all the variables that are present in the system, that including the number of phases and number of components. Okay. Now, what I do, the same equation I have rewritten here, whatever that equation that we have simplified in the previous slide, I have written like this. Now, the du is 0 at constant entropy, constant volume and then constant composition. That means what? Dou u by, let us say, dou S2, if you write, that should come 0, and then similarly dou u divided by dou v into, that should also come to 0 because at the constant volume, and then dou u divided dou u by dou n2 into that should also come to 0, and then dou u by dou s2 from this relation what you get? You will get T2 minus T1. Similarly, this using the same relation, if you do dou u by dou v2, what you will get? You will get P2 minus P1, and likewise if you do dou u by dou n2 2, then you will get mu 2, then you will get mu 1 in 2 minus mu 1 in phase 1, this is what you get. So, this since this is 0, so this should also be 0, this should also be 0, and this should also be 0. So, that means if T2 minus T1 is equals to 0, that means T2 is equals to T1. Similarly, you will get T3 is equals to T1, T4 is equals to T1, like that you get so many relations for all the terms, and then since P2 minus P1 is equals to 0, you will get P2 is equals to P1. Likewise, if you do for other terms, P3 you will get as equals to P1, and then P4 will also be equals to P1, like that you will get so many other equilibrium relations, right. Similarly, mu 1 into should be equals to mu 1 into 1, that you will get, because from here mu 1 into is nothing but mu 1 into 1 from here, from this relation. Similarly, mu 1 in 3 should be equals to mu 1 in 1, phase 1. Similarly, like that other components also, if you do the mu 2 in phase 2 should be equals to mu 2 in phase 1, and then mu 2 in phase 3 should be equals to mu 2 in phase 1, and so on. So, like that so many relations you will get depending on the number of components and number of phases that are present in the system. So, what does it mean? That means here from these relations you can get mu I in phase 1 should be equals to mu I in phase 2 is equals to mu 1 in phase 3 is equals to, and so on. So, mu I in phase alpha if there are a number of if there exist alpha number of phases, or pi number of phases, or n number of phases, whatever you will call. Now, it says that chemical potential of each component is same in all the phases which are coexisting and are at equilibrium. So, that we have proved it. In addition to this one, we have also proved that the if the process is in internal equilibrium with respect to heat transfer, temperature in all the phases is equal, and then also if the process is at internal equilibrium with respect to the displacement of volume, that is mechanical equilibrium is existing, then pressure in all phases should also be equal. That is also we have proved here. In addition to that, whatever the chemical potential of each component in all the phases should be equal. So, other thermal equilibrium and mechanical equilibrium relations are also proved. So, at equilibrium, whatever the thermal equilibrium, mechanical equilibrium and chemical equilibrium relations are there, all of them are proved here. So, now it is no ambiguity, or there is no confusion that the chemical potential of each component in all phases which are coexisting should be equal. So, that we have proved. The references for this lecture are Engineering and Chemical Thermodynamics by Koretsky, then Molecular Thermodynamics of Fluid Phase Equilibrium by Prosnich et al., and Chemical, Biochemical and Engineering Thermodynamics by Sandler, and Introduction to Chemical Engineering Thermodynamics by Smith et al. However, the details that are present in this lecture can be found in this particular reference, that is Prosnich et al. Thank you.